everyone, and thanks, Tao, for the kind introduction. First of all, I would like to thank the Technical Committee of Security and Privacy for awarding me with the Best Student Paper Award on these topics. And I'm really honored for this award. And then I would like to thank the Early Career Committee for giving me the opportunity to present my work here in this seminar series. What I'm going to present today is joint work with my PhD advisor, Frank Allgöver, and my name is Sebastian Schlor, and we're both with the Institute for System Theory and Automatic Control at the University of Stuttgart. In this seminar series, we look at topics in control systems with a special focus on security and privacy. And after last week's talk by Yannis, this is again clearly a talk focused on privacy. We're namely looking at encrypted control. Now, what is encrypted control? It's basically just a control loop between a system and a controller, but every measurement that we take from the linear system is encrypted before it is sent to the controller. And then the controller has to do all the computations necessary for the next control input based on encrypted data. And then only the control input is decrypted at the system where it is applied. And this procedure enables us to outsource controller computations to, for example, cloud computing services without any privacy issues. Now, specifically in this talk, I would like to talk about dynamic controllers, encrypted dynamic controllers. I will show you why having dynamic encrypted controllers is a challenge, and I will show you how a method from cryptography called bootstrapping can overcome these challenges but potentially introduces errors in this encrypted controller. And of course, errors in a closed loop can lead to catastrophic results, so we have to carefully analyze that, and will be the main topic of this talk. In the end, we will be able to give guarantees for the entire closed loop system, including the bootstrapping operation. But before I start with the technical details, I would like to begin with a quick motivation why dynamic encrypted controllers or algorithms in general are interesting. Since this is an online talk, I can't see you, but I'm sure many of you have a smartwatch on their wrist. And those devices are quite practical. You can continuously monitor your health. You can track your sleep, and you see your heart rate all the time. And since the companies that produce those devices want to save money, they put rather cheap, inaccurate sensors in these devices. But what they can do is simply they send every measurement they take to the cloud, and then there they do a sensor fusion and then get a more accurate result of the values that you actually want to measure. And this sensor fusion can be done with a Kalman filter, for example, as we all know from our control classes. And this is now very, very handy. You can always retrieve all your health data from the cloud on any device. But what about privacy? What happens if the cloud gets hacked and suddenly your personal data, your personal health data is available in the darknet for sale? Or what happens if the cloud uses your personal health data for targeted advertisement? Or maybe the cloud would even sell your health data to your health insurance that then has a special pricing just for you and your healthy or unhealthy behavior. So we clearly don't want that. But what would be the solution to that? And one solution that we can think of is simply encrypting every measurement we take before we send it to the cloud, similar to the encrypted control that we had on the first slide. With this, the cloud would have to compute on this encrypted data, so to evaluate the Kalman filter on the encrypted data and do the sensor fusion and all the statistics you need. And this would really enable us to provide a control, or in this case, a monitoring as a service without violating any privacy constraints. But maybe you're wondering, how is that even possible? How can you really compute on encrypted data? Data is encrypted and then you can't see anything on the data. And fortunately, cryptographers have invented homomorphic cryptosystems. Now, this homomorphic encryption enables us to compute on data while the data is encrypted. And this is called homomorphic encryption because it really preserves certain operations through the encryption. For example, here we can see you can encrypt two numbers, x1 and x2, and then you apply a special operation on the ciphertexts that if you decrypt the result, you get the same as if you added the two numbers in the first place. And here I'm going to present you a little toy scheme that just gives an impression how this homomorphic encryption could work. Of course, this is not a true crypto system, but it gives you a little insight how this is even possible. So first we need to pick an encryption function. And in this toy example, we simply pick e to the power of the number we want to encrypt. Then we also need this special encrypted addition operation. And for this, we simply pick a multiplication. Now, from our math classes, we know that the product of e to the power of two numbers can also be written as e to the power of the sum of the exponents of these separate exponentials. And now we also have to pick a decryption function. And for this, we can simply take the logarithm of the ciphertext that we have here inside. So if we look at this, then the logarithm and the exponential cancel out, and what we get is simply the addition of the two numbers. So this gives a little insight how such a homomorphic crypto system works, how we can really preserve this operation. And of course, this is not a secure crypto system, but if you add a modulus here and there and you restrict your numbers to a finite number of integers, then you're already quite close to a true homomorphic crypto system. And of course, there are many other variants of this. This would be an additively homomorphic crypto system because it preserves the addition, but there are also multiplicative homomorphic crypto systems that preserve the multiplication. And there are also many variants of combinations thereof. Okay, but back to the motivation. We wanted to evaluate an encrypted Kalman filter in the cloud or an encrypted controller, an encrypted dynamic controller. But we could also think of recursive least squares or a Luenberger observer or many algorithms of that kind. And I call them dynamical algorithms because essentially all of them are a dynamical system. And they all have in common that they have a recursion built in. Now, if you look at the state of this dynamical system that we are simulating here, this state gets updated over and over again. And if you let this system run indefinitely, then you need arbitrarily many operations that act on this internal state. On the other side, we have homomorphic encryption. And why we use them is, of course, they need to be a secure crypto system. Many of them even are post-quantum secure. And why they are useful for our purpose here is also that they support encrypted computations. Specifically, they support a finite number of encrypted additions and multiplications. And the limit, this finite number of multiplications in particular, depends on the level of this homomorphic crypto system. So by this level, basically the number of multiplications is limited. So in essence, these leveled homomorphic crypto systems support a polynomial of a fixed degree bounded by the number of multiplications to be evaluated on encrypted data. Now, we see a discrepancy here. Here we need arbitrary many operations, and here we only can evaluate a fixed polynomial, a fixed degree polynomial. And in the first introductory part of this talk, I will tell you why having arbitrary many operations is a challenge for homomorphic encryption, and then how this method called bootstrapping can extend this leveled homomorphic crypto system to a fully homomorphic crypto system, which really can do arbitrary many operations. By this bootstrapping operation, however, we possibly introduce some errors, and these errors have to be analyzed in the closed loop because this can be dangerous. So in the main topic, in the main part of this talk, we will then analyze how we can give guarantees for control, dynamic encrypted control with bootstrapping in the closed loop. Okay, so first to the challenge why having arbitrary many operations is a challenge for homomorphic encryption. And it's actually a whole chain of problems and solutions that cause new problems and new solutions. But let's start from the beginning. Most homomorphic crypto systems only support integers. This is because the underlying mathematical problem that gives security to the crypto system requires integers. But in control, we usually deal with real-valued measurements. So how can we deal with that? We can simply take our real-valued measurement m real, and then we scale it by a scaling factor, typically larger than 1, and then we round the result. This then gives a quantized version of the real measurement that we have, that is an integer now. And of course, we have to remember what scaling factor we used in order to decode it correctly. But then we are having a dynamical algorithm, which means that we over and over multiply something to our state, or we update the state in any case, which could lead to a growing scaling factor. Namely, if we look at the multiplication of two ciphertexts that both have a scaling factor s, then the result of this multiplication will have a scaling factor of s squared. And if we continue that indefinitely, then we get an ever-growing scaling factor until we get overflows and simply can't represent our numbers anymore. So what is the solution to that? In plain text, we would simply divide our new ciphertext or our new product here by s to restore our original scaling factor. And we can also do the same thing on the ciphertext. This is called rescaling. So we divide the ciphertext that has a scaling factor of s squared by s, and then we round the result. And the result really has the scaling factor s again, which then can be multiplied again, and we can continue our multiplications. The only problem is every ciphertext has a number attached to it, here this QL, and this is called modulus. So every encrypted number is interpreted with respect to this modulus. And if we divide our ciphertext by s, then we also have to divide the modulus by s. And this is here depicted by the change from QL to QL minus 1. And this L in particular is the level of the crypto system at the current stage. So this means if we divide by the scaling factor, we reduce we downscale our modulus, and it loses one level. And if we do that over and over, then the modulus decreases over and over again. And at some point, the modulus is too low, such that we can't represent our numbers anymore. So we have to increase the modulus again for being able to continue our multiplications. So this modulus decrease is a problem. How can we increase it again? And one solution to that is if you are at a low modulus, let's say lowercase q, then you simply interpret the same ciphertext in a higher modulus capital Q, and then you can try to continue your multiplications. But if you simply interpret the ciphertext with respect to a new modulus capital Q, then if you decrypt this ciphertext with the new modulus, then you get your original number that you encrypted plus or minus some integer times the original modulus of the ciphertext. So you essentially get an offset to your true number that you encrypted. Now, how can you get rid of this offset? This is the essence of this bootstrapping operation. Namely, you evaluate the modulo q function on this ciphertext in order to remove this integer multiple of q as an offset from the true number that you encrypted. Okay, so maybe let me summarize this quickly again. Since we only deal with integers, we have to introduce a scaling factor for our real-valued measurements to be encrypted. And if we multiply two numbers, then we increase the scaling factor. We can rescale the scaling factor, but then we also reduce the modulus. And at some point, the modulus is too low, such that we have to increase the modulus again. And this can be done by this interpretation, but we get an offset. And to reduce the offset, remove the offset, we evaluate the modulo function, and then we get the correct m again. And then we can continue our multiplications from the beginning. So this is the modulo function that we actually want to evaluate on the ciphertext. Here we use a modulo function that is centered around 0 just for symmetry. And here you see different offsets. So here we have 0 offset, here we have offset of 1q, offset of 2q, and the same thing on the negative side. So our true number lives in this area, but it could be offset to any of these sections. And by applying this modulo function, we remove this offset, and map it back to this interval. Now, maybe you remembered that I said in the beginning we can only have additions and multiplications on encrypted numbers. With this, we can evaluate any type of polynomial, but what we have here is a piecewise linear function, and exactly this piecewise makes it hard for encrypted computations to evaluate. Namely, we can't simply compare numbers, which is necessary to have these jumps here. So we cannot really evaluate this modulo function. The only thing we can do is we can find a polynomial approximation of this modulo function, and this is what we can really apply in practice. Now, by this polynomial approximation of the modulo function, of course, we make an error, and this error we have to carefully analyze. So this brings me to the main questions in this talk. How would we possibly, in a smart way, choose this approximating polynomial? And then how can we use this polynomial and the errors that we get to really give guarantees for the encrypted closed loop system, including the bootstrapping? So let's start with the first part. How do we choose this approximating polynomial? First of all, we have to make an assumption in which areas we want to approximate the modulo function. And for this, we make two observations. One is that we assume our message that we want to encrypt lives in an epsilon area around 0. So this basically is depicted here by the gray areas. Around every root of this modulo function, we have an area that contains our numbers, and we assume our numbers are not present in these higher values. And then the second observation is that the offset, so the number times q as an offset, is bounded by some k. This can be verified, or this can be designed by the type of a secret key we choose for the crypto system. So in this case, k would be 2. We can have 0 offset, 1 offset, or 2 offset, but no more than that. Okay, so we want a polynomial approximation of the modulo function in the gray areas here. And in the literature, there are many heuristic solutions, and they are great for general applications because they are quick to evaluate, but they don't give any error bounds. Then there are some approaches that try to bound the maximum pointwise error between the polynomial and the modulo function. There are also works that try to minimize the variance of the error between the polynomial and the modulo function. What we propose as a solution especially for encrypted control, is to use a sector-bounded polynomial. That means that we bound the error between the polynomial and the modulo function by a term that is linear in the true value we wanted to have. So the error is bounded by gamma times the absolute value of this modulo function. And why do we choose this sector bound? Simply because control systems can really well deal with sector-bounded uncertainties and disturbances. And this is what we can use for giving guarantees at a later stage. So here we see the same picture as before. We see the modulo function. We see the polynomial that approximates the modulo function in the relevant areas. But now we also see this orange cone that describes the sector bound around the modulo function in which the polynomial approximation always lies. So no matter in which offset we get and in which section we are here, the polynomial always remains within this orange sector bound around the modulo function in the relevant area. Now, if we look at the error between the modulo function and the blue polynomial, and we overlay all of them, all of the sections here onto one interval, then we get this picture. Here again, we see the orange cone that describes the sector bound on the arrow. And in blue, we see the different arrows between the bootstrapping polynomial and the modulo function, depending on in which section of the modulo function we are. So we have different arrows depending on the offset, but all of the arrows remain within this orange sector bound. And this is what we can now use to giving guarantees. But first, you may be wondering, how do we obtain such a polynomial? And one method to doing so is using sum of squares optimization. So we can simply write down an optimization problem where we minimize over the slope of the sector gamma, subject to the constraint that the polynomial, so the error between the modulo function and the polynomial, remains within these bounds for all the values inside the gray epsilon intervals that we had for all possible offsets. And with this optimization problem, we could, for example, design the polynomial that you just saw in the previous pictures with the degree 25 for a given overflow of 2 and the relevant number range of 50% of the whole interval. And with that, we got an error bound that states no matter in which section we are, which offset we get, we always have an error that is not larger than 23% of the actual number that we encrypted. Okay, now we have this. Now the question is, can we do control with it? And what are the guarantees that we can get? And for that, we look at an encrypted control setup where we have a linear system with an state X. We encrypt every measurement that we take from the system. We send the measurement to the controller. The controller is a dynamical controller, so a dynamical system with its state xc. And it evolves according to its linear control laws. Then the control input is generated, sent back to the linear system, decrypted, and applied to the system. And from time to time, after we've done a number of multiplications, we have to increase the modulus again. And for that, we apply the bootstrapping on the entire state of the controller. And then this new state after bootstrapping replaces the original state of the controller as the new state. And of course, this contains an error. So this error has to be analyzed in the closed loop here. So let's look at in more detail about on the equations. So here we see the equations of the controller. The controller state at the next time step depends on the current controller state and on the measurement of the system. And then the next control input also depends on the current controller state and the measurement. Now, if we start at time equals 0, we simply do the update of the controller state. Then we do the same thing at time equals 1, and so on. And we do that for a couple of time steps until we consumed all the levels. So we have to increase the modulus again. And for that, we apply bootstrapping. So basically, we enter every component of the state inside our bootstrapping polynomial to remove the offset that we don't know. And then we get a new state that is approximately the same as the state of the controller before, but it contains some error. And with this new state of the controller, we now continue our computations and update the controller at the next time step. Okay, now with this, it's hard to see what happens with this error, but we can also write this bootstrapped state at the next time step as the exact controller state plus some delta that now describes the bootstrapping error. And with this decomposition, we can also write the next update step of the controller as the true update we would like to do, plus a term that again depends on the bootstrapping error. And with this decomposition, we could simply add this term also to the controller update equations here, where we now introduce an uncertainty channel. So we basically introduce an uncertainty output that is the entire state of the controller. Then we have an external uncertainty that is simply describes the bootstrapping error. And then this bootstrapping error enters the next controller state update as an uncertainty input multiplied by this matrix AC of the controller. So with this, we have introduced the bootstrapping error as an external uncertainty, and we can now use our uncertainty, our linear sector bounds to describe this uncertainty for an analysis with robust control techniques. So now, again, let's look at the overall setup. We have our system, our controller that are interconnected, but now the bootstrapping is not just an unknown or an hard to describe process, but now we have an uncertainty output of the controller that enters the bootstrapping, and this uncertainty here is now described by our sector bound as an uncertainty, and then the result of this uncertainty enters the controller again with the known dynamic matrix of the controller. What we can do in addition is we can introduce a performance channel. So we can introduce a performance input on the system, and we can introduce a performance output on the system. And in addition, we can also introduce a performance input to the controller, which can be used for analyzing the effects of other errors that can occur in the encrypted control loop, for example, due to quantization and also due to encryption. There are also some noises added for security reasons. So with this setup, we can now, first we need a better description of the bootstrapping error that is more suitable for the analysis now. So instead of having the sector bound as we had it before, we can also rewrite the sector bound in this quadratic form where we have the uncertainty input to our system here, so the uncertainty, the output of the uncertainty, and the uncertainty output of the controller in this quadratic form. And we know that every bootstrapping error satisfies this inequality, where the slope of the sector bound enters here inside this matrix in the center. So this again describes the sector bound on the bootstrapping uncertainty, and this is now in a perfect shape for a robust control analysis. Okay, this brings me to our first theorem on this interconnected system. Let's say we're given the plant, so the linear system and the controller, and then we determine a sector bound on the bootstrapping polynomial that we are using. Then our theorem gives the following result. If our robust analysis linear matrix inequalities hold, then we are guaranteed that the overall system consisting of the controller and the linear system, including the bootstrapping in closed loop, satisfies stability and a given performance. So with this, we transformed this unknown bootstrapping error in such a way that we can analyze it as an uncertainty in our a closed loop, and with these robust analysis linear matrix inequalities, we can now give a guarantee on the stability and performance of the overall system. Now, with our reformulation as an uncertainty, we basically analyzed bootstrapping if it would occur in every time step, although we only do it every capital T time steps when we consumed all of our levels. So it would make sense to only add the uncertainty in our analysis then. And for this, we introduce a new time index called K here that basically only looks at the dynamical system or at the closed loop system at times where we really introduce the bootstrapping error. Here we see the equations for the closed loop. So this xi here is a combination of the state of the controller and the state of the system that we control. And the next state depends on the current state, the performance input, and also the uncertainty input. And here we would really introduce the uncertainty in every time step. But with our lifted system, we can describe the overall closed loop system only at these at this new time index k. So we can take the dynamic matrix A to the power of this capital T. We can stack all the performance inputs into a new vector of performance inputs. And we can only add the uncertainty resulting from the bootstrapping at this one time step where it really occurs. So with this new lifted system analysis, we again are given the plant and the controller. Then we reformulate this as a lifted system that only looks at the bootstrapping at times where it really occurs. Then again, we determine the same sector bound on our bootstrapping polynomial. And with this theorem, we now get a less conservative result. Namely, we have robust analysis linear matrix inequalities. And if they hold, then again, we are guaranteed, we have stability and performance guaranteed for the overall closed loop system, but now with less conservative results. We also have a numerical example here where we analyzed a chemical batch reactor with a PI controller, which is a very common example for these dynamic encrypted control systems. We assumed that every 25 time steps, we have to do bootstrapping. Then we used our sector-bounded polynomial that we use all the time here in this talk. And as a performance measure, we wanted to find an upper bound on the L2 gain. And what we got as a result is that our theorem without lifting led to an unfeasible solution. So that means, with this theorem, it was too conservative. We don't find a solution. We can't give any guarantees. And in fact, if we simulate the system where we introduce the bootstrapping error in every time step, then we really get an unstable system. On the other side, the theorem with lifting led to a result, and we could find an upper bound on the L2 gain of 11.4. For a comparison, the nominal system without the bootstrapping errors has an L2 gain of 10.4. So with our theorem, we're not too far off, and we can really give guarantees for the overall system, including the bootstrapping. Now, instead of bootstrapping, there are also other works that propose different solutions to this problem. And one solution is simply if you are at the end of the possible multiplications, then instead of doing bootstrapping, you simply reset your state to a known encryption of 0. And with that, you also restore all the new levels that you had in the first place. Another idea was to use finite impulse response controllers that don't have arbitrary many operations acting on the state, but only a finite amount of them. And if we look at this reset controller, then resetting the controller simply means you subtract the entire state from the state that you had before. So you make an error of 100%. And this can also be depicted here in our known error bound here by having an error that is negative identity here. And this error could also be described by a sector bound as we had it in our work. So in some sense, we can also generalize the analysis of this kind of reset controller with our tools. And similar reformulations can also be done for finite impulse response controllers in comparison to the dynamic controllers that we actually wanted to have. Okay, so as a summary, we can say that I introduced to you why we need bootstrapping in this dynamic encrypted control setups, because we, with every multiplication, we increase the scaling factor. We have to divide by the scaling factor, so we also decrease the modulus of the ciphertexts. We have to increase the modulus again, and to get rid of the offset that we get by the modulus increase, we have to apply the modulo function to the ciphertext, but we have to approximate the modulo function because we can only evaluate polynomials. Now, for the application in dynamic encrypted control, we proposed to use a sector-bounded polynomial. We proposed to reformulate this sector bound now as an uncertainty inside the closed loop. And then we could use robust control tools for a performance and stability analysis of the overall closed loop system with the bootstrapping. And finally, we could also use a lifted version of our theorem where we could reduce the conservatism of the result. If you are interested in more details, please have a look at our LCSS paper that is here behind this QR code, and there you find more results on the more details on our results. As an outlook, it would be very interesting to further investigate the following trade-off. So clearly, we have to choose a polynomial with a certain polynomial degree for the approximation of the modulo function. And if we increase the polynomial degree, we could find a more accurate result, but it takes more computational time to evaluate this bootstrapping operation. On the other side, it's maybe okay to have a less accurate polynomial if we have more robustness in our controller with respect to these bootstrapping errors. So this trade-off between having a high polynomial degree and good accuracy, but bad computation time, and also the robustness of the controller is an interesting topic to explore. And further, we could also analyze other errors that occur due to quantization and encryption. So far, we only did this through this second performance input here to the controller. Now, before I come to the end of my talk, I would like to give a bit of a broader view on the topic of encrypted control. It has existed now for almost, for pretty much exactly 10 years. And from the very beginning, we were basically able to encrypt static controllers. And there are many different versions how we can do that. So this is a solved problem, I would say. Then, in the meantime, we're also able to encrypt dynamic controllers. One method I just proposed here to you. But there are also other methods like this resetting controller, the FIR controller. And there are also different integer reformulations that don't need bootstrapping or resetting. So I think this is also a more advanced stage of research. What I see still as a potential open problem in the future is encrypted model predictive control in the single cloud setting. Of course, there are already some encrypted MPC papers out there, but most of them need a second cloud, for example, for a multi-party computation setup or a trusted third party, or sometimes also the system itself has to do part of the computations. But for the single cloud setting, I think there's still open questions. And the particular challenge here for encrypted model predictive control is that it's hard to do encrypted constraint optimization. So for example, here finding the minimum of this red function within this gray area, within this gray interval, is a hard problem for encrypted computations. Because simply the main problem is that we can't compare numbers. And in last week's talk, Yannis already mentioned that he has some ideas about encrypted constraint optimization using his reliable matrix inversion and also ADMM. We have also been working on this problem, and we came up with a solution in the spirit of interior point methods, but only using polynomials. And we're going to present this work at the upcoming CDC, so stay tuned for this work. With this, I'm really at the end of my talk. I showed you how we can have dynamic encrypted controllers, including bootstrapping, and how we are still able to give guarantees on the performance and stability of the overall closed loop system. Again, I would like to really thank the Technical Committee on Security and Privacy for giving me the award. And I would again like to thank the Early Career Committee for this amazing seminar series. With this, I would also like to thank you for your attention. And now I'm looking forward to your questions.
Great. Thank you.